S3 day 2, section 11.3 dot product. So the dot product is the way to multiply vectors. Last class we looked at the way to add vectors and subtract vectors, which was done component-wise. We did that in 2 dimensions and 3 dimensions. We added the x components together, which were with the I unit vector in the direction. And then the next one was the j and then the k for 3D. We did that component-wise. We saw also that we can multiply by scalars so that we can extend or shrink those vectors. If we multiply by a scalar, we don't change the direction, we only change the magnitude of the vector, the length. We also learned about unit vectors, which were always magnitude 1, preserving the direction of the original vector. Today we're going to take a look at 2 different ways to multiply vectors. It is vector times a vector this time, not vector times scalar like last time. And the first one of those is the dot product. It's going to be a definition of how it's done. And then we have to understand that this is going to be a definition that can be extended to any dimension. So the dot product is going to be multiplication of the components, and we add all of it together. So dot product definition is that given 2 vectors u and v, the dot product is and I'm going to write both cases right off the bat. So u dot v, which is actually u1 comma u2 dot v1 v2 is equal to u1 v1 plus u2 v2. And in pink, the 3D case, u dot v, u1, u2, u3, dotted with v1, v2, v3 is u1, v1 plus u2, v2 plus u3, v3. Note that the answer to multiplication of 2 vectors using dot product is always a scalar. So we are going to write that also. Well, not result. Let's use the product. Now, vectors extend in multiple dimensions. When you have only magnitude, no direction, well, that's just numbers, and you know those. So when you have 3 times 5, well, that's just 15. But technically, guys, it's a vector 3 times the vector 5, and since it only has 1 component, it multiplies into 3 times 5, and it's 15. If you have 2 vectors that need to multiply, so let's say 2, 1, dotted with 8, 3, in that case, it's going to be 2 times 8 plus 1 times 3, and that gives us 16 plus 3 is 19. And for the 3D case, 2, negative 1, 4, dotted with 5, 4, and 2, whatever. we have 2 times 5 plus negative 1 times 4 plus 4 times 2, which is equal to 10 minus 4 is 6 plus 8 is 14. So when we multiply two vectors using the dot product, we get a scalar quantity. This is the multi-dimensional multiplication you already know. I started with 3 times 5 is 15, and then you can think of those 3 and 5 as vectors, actually, and those vectors will have no direction because they only have the magnitude. So it's only the x, right? The x component. It's like 3i, but not I imaginary I, the 3i in terms of the unit vector I, times 5 over there, and we get 3 times 5, which is equal to 15. So you know that case. This is something that you covered. No one ever talked about it in terms of vectors. And then now we have upgrade. What happens if you have two-dimensional vector? What happens if you have three-dimensional vector? What happens if you have four-dimensional vector? And so on. The dot product will work in every dimension. Doesn't matter. You can go as high as you want. Now let's take a look at the use of this dot product, because we don't define things just to have them, right? We define them so we can use them in engineering, physics, and so on. So what can we do with this? Well, we can actually find the angle between two vectors using the dot product. If we multiply the two vectors and divide by the magnitudes, we can find the cosine of the angle in between them. Now we can draw that picture. Let me write the formula first, and then we can take a look at the picture and try to understand why this works the way it works. We have u dot v is equal to magnitude of u times the magnitude of v times the cosine of the angle in between them. From where you can solve this, right? So this is the formula on its own, but then you can solve this into theta is equal to inverse cosine of u dot v divided by magnitude. So this is the same formula, just flipped around. And you see that you can find the angle between two vectors quickly if you know that formula. So angle between two vectors. And the great thing is that dot product does not restrict which dimension you need to use, so you can use any dimension you want. Would this work on the one-dimensional thing? Of course. You have 15 divided by 15 is 1, and inverse cosine of 1 is 0, because there is no 2 on the number line, or you can think of a pi, doesn't matter. On the number line, the angle between them is, let's say, 180 degrees. You can use that. There we go. So the angle between two vectors, this is the 2D case. And we can find that angle. Let's go with the example. And you can use degrees because it's going to be, these are quick calculations to start off the day. So what's the angle between these two vectors? No pressure, you have 17 seconds. Okay, so Last class we learned how to find the magnitude of each of the vectors. So we'll need the magnitude of u, which is 3 squared plus negative 1 squared plus 5 squared, which is 9 plus 1 plus 25, which is square root of 35. Magnitude of v is going to be 1 squared plus 4 squared plus negative 3 squared is equal to 1 plus 16 plus 9 is equal to square root of 26. And now we have that theta is equal to cosine inverse of the dot product. I'll write 3, negative 1, 5 dotted with 1, 4, negative 3 square root of 35 times the square root of 26. So I have 1 minus 4 minus 15 divided by square root of something. Now what we're going to do is we change the calculator into degree mode. There is an app for Droid-based phones, and you can download all of the TI versions on it. Yes. That's what I said. Please pay attention. This clearly says 3 over there. Thank you. 35 times 26 square root of 910, so it's about 30. Oops, cosine inverse. So cosine inverse negative 16 over the square root of 910, 30.2. This is roughly negative 1/2. But we'll use the cosine inverse. So mode, and in mode we go into change it into degrees. You can't graph in degrees, so you need to graph in radians, so you'll be switching back and forth depending on what you need. Oh, actually, wait, you can't use calculators on the test anyway, so whatever. Divided by 910. Inverse cosine. Yeah, negative 16 divided by 30.2. There we go. About 122 degrees. So theta is about 122 degrees. We will see later that these vectors, two vectors, define a plane, and no matter which way you have two vectors in space, so here we have a vector and another vector. No matter which way you put these two vectors in space, you can change the angle, you can change which way they are. There will always be a way to associate a plane to those two vectors. No matter which way, what's the angle between them, and which way they look, there is always going to be a unique plane going through those two vectors. So, since whether it's 3D or 2D or whatever D, you will always be able to do that. That means that the angle between them can be computed. Remember that we did not talk about the direction of a 3D vector, because there are many things that you can compute in terms of how direction works. We only define the magnitude for it. So With this formula, you can compute the angle between any vectors in any dimensions. So we have the dot product, we have the... Now, what is the consequence of the formula such as this, where the u dot v is equal to u times v times cosine theta? If we have this, that means, that we can find if the dot product, what happens if the dot product is 0? Right? If the dot product is 0, then we have that 0 is equal to u times v cosine theta. But then these two guys cannot be 0 because the vectors, unless they're 0 vectors, the vectors have the magnitude, the length. We also saw last time that the 0 vector is in the origin and it has no direction. So we cannot talk about the angle between a 0 vector and something else because 0 vector technically collapses into a point at the origin. So we have to exclude the case that either u or v are 0 vectors, which immediately excludes the possibility of magnitudes of u and v to be zeros. So if u dot v is 0, but magnitudes cannot be 0, that must mean that cosine theta is 0. And that happens when? When theta is 90 degrees, pi over 2 radians. So u dot v equals 0 implies that u is perpendicular to v. We say orthogonal. Orthogonal is the word we use because perpendicular is for two lines in a 2D space. And if you have a 3D space or 4D or whatever D, and two vectors are at 90 degrees between each other, we say orthogonal. So two vectors are orthogonal if the dot product is 0. Now this actually extends later depending on how much you are going to push with math. There will be also discussion in linear algebra about notion of orthogonal functions, where you can actually check for orthogonality of the two functions. So you will find out that sine and cosines are orthogonal, and so on. There are many others, but you will find some of that stuff down the line. Right now we're only dealing with vectors, so you simply do the dot product. If the dot product is 0, the two vectors are orthogonal, and you're done. We are moving along. The cool ones for this would obviously be your unit vectors, I, j, k. So you can prove that all of these are 90 degrees or orthogonal to each other if you do the dot product, and the dot product between any of those cases will always be, let's go, I and k. Remember, I'm using hats instead of arrows because unit vectors are denoted with hats, and I, j, k are unit vectors. So I have 1, 0, 0 dotted with 0, 0, 1, which is 0. So dot product is 0. That means that I and k are orthogonal, which we know they are, because one is on the x-axis and the other one is along z-axis. Dot product, that's all done, that's defined. Next is the properties of dot product. So what are the properties of dot product? We have commutative property, associative, and distributive properties. So u dot v is equal to v dot u. So it's commutative. 2. Associative property, c u dot v. So c is the scalar, just like last class. So we have cu dotted with, v. Or u times cv. So this c is just going to scale it, and you obviously use it only on one, not on both. You're not distributing. Next is distributive property. And distributive property is u v plus w is uv plus u w, and that would be the distributive property. How do we prove this? In your case, we have the u1, v1 components, multiply, switch the order when it's regular multiplication you used to, and then bring it back. So the same, along the same lines like the stuff last class. And now we have orthogonal projections, which ends the section. So the textbook has a nice graphic for it. So I'm just going to show that real quick. As you can see, there are two vectors. There is a vector on a desk, right, on a table. That's that blue vector v. And then there is that red vector that is above the desk at some kind of angle. So something like this, right? So you have the vector v, and the vector u is on the desk. You shine the light on the top, it casts the shadow onto vector v, which is on the desk. So what is the projection? Projection is the amount of shadow that the red vector casted on the blue vector v. That is what it is. Now, why would that be important? It has huge physical applications. So consider pushing a block or doing some kind of work like that. You don't get to use all of your force to push the block. When I say force, I don't mean the force, you know. The way you interact with the object and the angle at which you interact with the object is important. And all of that is encoded in the formula that I will shortly show. So if I have an object that I have to push, like this chair, for instance, let's say this is very difficult to push, right? If I take the stand for pushing, right, really hard, it might look like this. Now observe the angle at which the force is applied. You see, this particular vector in which I am applying the force to the object can be decomposed into a vertical component down up to the chair level of the chair, right? So about that much, right? That much down. And then there is also the forward component. Now, both of these components are shorter individually than this one, which means that this force is broken into those two perpendicular forces, force straight down and the force straight forward. But I don't get to bury this into the ground, right? So all of that force that is pushing the chair down is wasted because the chair is not going down. So only the shorter force, the forward force, that is perpendicular to the floor is the one that pushes, which means that this much force is wasted. if you want to have a perfect push, and you will see people do that, you go like this, right? And then it's straight, parallel with the floor, which means that all of the push, 100% of the force, is going into pushing, and none of that goes into trying to bury the object into the floor, like when you're pushing like this. So anytime when there is something heavy that you have to move, the more perpendicular your arms are to the floor, sorry, perpendicular, the parallel to the floor, the more force goes towards pushing the object, and the less goes towards the waist in terms of trying to bury that object in the ground. Also, it goes on for lift, right? If you are lifting this way, it's much harder than if you're lifting this way, because, again, that's unless you have to push up and forward. So pushing only up goes that way. I forgot the chair. Gotta go back over here. So these orthogonal projections are taking care of figuring out those smaller forces that are actually doing the work and discarding those that do not. So when you are looking at the graphic over here, if this was the force that it's actually pushing, sorry, this is the force with which you are pushing, this one over here, the projection, is the one that is actually doing the work, and the rest is wasted. So there is a formula that can be derived from these pictures. Our honors section will obviously read that and be responsible for that derivation. The rest of you just need to know the formula and how to apply it. So the derivation is fairly simple. It is 3 lines. And the projection is where? The second one. There it is. So projection of U onto V. So vector U is the main vector and V is kind of the guiding one. We go with projection of vector U onto V. It's like a log notation, right? You have the base. Oh, yes. Details, details, details. So projection of U onto V is projection of U onto V. V is the index. Is going to be U dot V divided by U dot U. So that's all going to be a number. And, oh, sorry, these are V's, because we need the directions. There we go. And then times vector V. So let's see. 2-dimensional case, 3-dimensional cases. Just plug in the formula and just grind through it. 2, 5. And V is 1, negative 3. All right, let's project. All set? So projection of vector u onto vector v is, we have u dot v on top, so 2, 5 dot 1, negative 3 divided by, now v squared, that's the magnitude of v. So I have 1, negative 3 dot 1, negative 3, all of that times 1, negative 3. So as we compute, we have 2 minus 15 is negative 13 divided by 1 and 9 is 10 times 1, negative 3, and when you distribute this, we get negative 13, 10, comma 39, 10. And if you really want to use the ugly decimals, you can say negative 1.3 and then 3.9 if you really must. But this is okay. Now let me see if you understand this. I'm going to ask you, this vector here has the same direction as which vector? U or V? V. Has the same magnitude as which vector? Me? None of them. That was a trick question. If you look at the graphic one more time, here it is, you will see that the vector v, vector u, and the projection vector all have different magnitudes. They have to. Do we all see that? So in this particular case, vector v is the longest, vector u is in the middle, and the projection is the shortest of all. The larger the angle, the shorter the projection. Which makes sense, right? Because with the, imagine, right, it should show the force that is actually doing the work, right? It's actually pushing. Now look at this. Right? It's a very steep angle here. There is a very short vector that is actually doing the work of pushing the chair forward. It's very difficult to push this way. Now, much better, right? And if you can have it parallel, the best, obviously, because 100% of the force goes towards pushing. So these are our projections, and you will learn the formula. And now we can define the work, which is exactly what I was talking about. So we're going to use the same formula, just change the letters. Yes?
I do know the direction.
Because it's a projection onto v vector, so it carries, the v vector carries the projection. If you carefully look at the picture, oh, this picture is there. If you carefully look at the picture, you see that the projection vector, which is that little gray vector that you can barely see, is overlapping on v. So whatever the direction of vector v is the direction of it sits on it. All right.
Is it always going to be the same as v?
Yeah, because it's projection onto v, right? So it's. Yeah. Well, depending, yeah, which way they're oriented, could be y, right? It goes up. Work. So application, the work is going to be force times the distance. And you learned that in physics, force times the distance for work. But then it's also times the cosine of the angle, because I just explained pushing the chair or pushing the fridge or pushing whatever is going to be always dependent on the angle. The steeper the angle, the less force you are exerting at the object, so it's harder to push. So work W is going to be the force, which is the vector, dotted with the distance, which is also a vector. Distance is going to have a direction in which you are pushing and how far you go. So it's also a vector, distance you're covering. So we have the magnitude of the force times the how far, right, the distance you have to cover, times the cosine of the angle in between them to take care of the situation, the way you push. And then calculating work, all you need to do is to plug vectors in, so you will get an example. They gave a nice 3D example in the book. We can look into that one, or we can do something else. Let's see. Do they have anything in the homework section that we can look at, because you can read the book hopefully? Oh, beautiful. Yeah, I forgot how wonderfully approachable this book is. In the section for projections, all they did is they gave you all of the chapter 14 questions. That's how lazy they are, actually. Can you please lift that one more time? Guys, if you really want to have a book that you can read, that book is only 10 to 15 bucks online. The 7th or 8th edition, that's 8th edition. 7th. Okay, a 7th edition. So 7th edition or 8th, it's only cost 10 bucks or 15 bucks. I think they're at 12th edition now, which is the one that's going to cost over $200. I learned from that book and the one before that. And it's very easy to read, very easy to understand, and they have problems that you can actually do. This book has a very, very simple problems, and then opens the gates of hell, because the flow in a circle and the heat flux is all in chapter 14. All of those concepts, they're vector fields, so we have to cover a lot more stuff before we actually venture into these things. Yeah. Exactly. Where are the work? Do they have a single work problem? Yes, there they are. Okay. A stroller is pushed 20 meters with a constant force of 10 newtons at an angle of 15 degrees below horizontal. So a stroller looks like a grill until I put this, and now it's a stroller. You see that? I put some rims on this thing. I know. It's only supported here, so it can actually rock. I'm a master in design, so there we go. An ergonomic handle right there. Should put a joystick there and a pad with buttons, so actually you can just do that. It goes. All right. A stroller is pushed 20 meters, so it's going to go 20 meters with a constant force of 10 newtons. Oh, sorry, that's bad. This is the horizontal, and then 15 degrees below horizontal, 10 newtons. Who's pushing this? I think the kid is actually pushing. The adult went into the stroller and the kid is pushing it. There we go. We solved the mystery. All right, so I mean, if you are at 15 degrees below pushing the stroller, you shouldn't be pushing the stroller. You should be pushed in the stroller. All right. So now we compute this. Right? We have the formula. We just plug things and we're done. So what's the work? Work is magnitude of the force, which is 10 newtons, times how far you're going, times the cosine of 15 degrees. Now, is it cosine of 15 degrees? We have to be a little bit careful, right? The all students take calculus thing. We have 15 degrees there. So cosine of 15, 15 below 100. So what do we get? This thing is still in the... No! Oh, actually, it's already done. For those watching the stream, I dropped the marker. No one died. Don't worry about it. No need to call the police. I panic when I drop the marker. All right, so this is going to be 200 times 0.966 is 193.2 Newton meters. That's the work for the stroller. And then you get paid accordingly, right, for the work done. Which concludes the section on the dot product. Yes? Because cosine is the even function, so negative 15, positive 15 is the same answer. Sharif? Real quick. This is the quickest we can. A little further. Just for me to check the quadrants to see, make sure if the negative appears or positive appears, but then I remember that the even function, the cosine is even function, so whether it's positive or negative on a cosine. Yeah. Okay, let's just recap this and then go for a break, stop the stream, and then we'll resume the stream for 11.4. So guys, the dot product. The dot product is a way to multiply vectors. The answer is always a scalar. And if you ask me, what do we actually get when we multiply? We get a number. The same thing that you get when you multiply 3 times 5, you get 15. When you multiply two vectors in the dot product, you get 15 or 19 or whatever. The definition, u dot v is equal to u1 v1 plus u2 v2. So you will always multiply the corresponding components and then add all of the products. It works in any dimension, and product is always a number, a scalar. Examples for 1 dimensions, 2 dimensions, and 3 dimensions, where one-dimensional calculations match your basic multiplication tables. And now we have the biggest deal of all in the lecture is to find the angle between two vectors, because that is what is usually something you have to find. And the formula is given. which obtains the angle. We did the 3D example for 122 degrees. Here is the theorem. This is an important theorem, so maybe I should box it in pink. There it is. So it's an important theorem, and this theorem states that u dot v, if the dot product is 0, the vectors are orthogonal. They're 90 degrees. Properties with the commutative, associative, and distributive rule, and then orthogonal projections. Now, guys, make sure that you are learning these formulas, because that's what Calculus 3 is. Right, so let me just stop the stream. So you need to know these formulas other than physics formulas. Physics formulas we would provide if you need.